So there's some consequences to this here that are interesting, right? So if you're paying attention here, you'll notice there's a trick that just happened here. Classically, this is interpreted to mean that 1 over 0 is infinite. But clearly, that doesn't actually make sense. What this means is 1 over the number just to the right of 0, just to the positive side of 0, is infinite. And similarly, 1 over the number just to the left of 0 would be negative infinite. But 1 over 0, we didn't actually get an answer for what that is. This actually, it seems like it's a problem because it seems like it's contrary to what limits mean. But it actually saves us. It actually makes a lot of sense, right? Because, so if I drop this in here, limit of x approaching 0 from the negative side of 1 on x is negatively infinite, while this one is positively infinite. 1 on 0 is inevaluable. Right. Could be anything. It could be nothing. It could be everything all at once. It could have 17 solutions at once. It could have a billion solutions all at once. It could have any number of solutions all at once, including all of them or none of them. 1 on 0 is completely inevaluable. But the limits to the right and the left are evaluable. And this is important because this tells us what limits actually are. Limits are dealing with the ideal approximations of the thing that we cannot evaluate, right? They are not dealing with the thing itself. So when we're looking at something like 0 to the 0 power, and we're using limits and making arguments like, oh, well, the limit's indeterminate, so it must be undefined. No, that's not what this means. That's not what the limit is telling you at all. What the limit is telling you is that from different angles, as we come in to approximate it, there's a range of different answers that we can get from those different approach angles. That's all that means. None of them are actually evaluating 0 to the 0. None of them. So this makes sense of that. This actually capitalizes on that fine distinction. And it means that the entire endeavor of analysis of anything that's using limits, generally analysis is that branch of mathematics, but anything where you're using limits, you're not actually getting at the answer of, you're not getting at an evaluation of whatever it is you're looking at. You're getting very close approximations. But, as you can see here, with 1 on x, it can be discontinuous. Right? How do you go from positive infinity to negative infinity instantaneously? Well, you don't. You don't. There is a transition point between those two. Right? And that transition point is the thing that you cannot evaluate. If you don't find that beautiful, then I don't know I don't know what to do with you. And this gets deeper too, right? Because that 0 in the denominator there, what that's telling you is that you're trying to analyze something which is perpendicular to the dimension that you can actually see. And since it's perpendicular to the dimension that you can see, it's invisible to you. This guy, this ideal approximation of it, which isn't 0, is still visible. You can actually see it. You can see how it behaves. That's how we're able to evaluate this, and how we're able to evaluate this, and how we're able to discern that there is a discontinuity here. But the problem is, it's actually no more discontinuous than if, you had two values right next to each other. One yielded 3 and one yielded 4. Right? This must be distinct from this, by definition. And yet they're infinitely close to each other. They're right next to each other, but they must be different from each other in order for the function to change over values. There must be a difference between this value and this value. Right? Similarly, there must be a difference between this value and this value and this value and this value. This is a continuity here. It's just one that you've been trained to ignore. Right? So you can think of it like one of the common ways of looking at division by 0 is like taking a line and sweeping out a circle with it. Right? So as the line, and we're looking at the slope of the line, right? So you've got the line coming from the positive x-axis, and it's anchored at the origin, and the end point is moving around. The angle is increasing as you normally would in trigonometry, right? So the end point is swinging around, and as it approaches pi on 2 radians, 90 degrees, it's the slope of this line approaches infinity, right? But what happens when it exactly hits pi on 2 radians? What happens when it exactly hits 90 degrees, straight up and down? Is its slope infinite? No. Right before, immediately before it hit that, it was positively infinite. And immediately after it is negatively infinite. But at absolutely vertical, the question of what its slope is doesn't even make sense. It's invisible. Right? Because slope is dy dx. Right? Change in the vertical divided by the change in the horizontal. There is no horizontal change because none of it exists horizontally. It's completely vertical. Right? You only have horizontal away from this completely vertical thing. Right? So if we're just before completely vertical, now its slope is positively infinite. And if we're just after that ideal approximation of completely vertical, that is just after being vertical, just over pi on 2, that is negatively infinite. And suddenly, this all makes sense. Whereas before, it was just like random ass shit that didn't make any sense and you just kind of had to memorize because it seems to, it works out, it pans out when you do when you do calculations. Like, these values are the ones that it has to be, because these are the ones that work. Now there's actually reasoning to it, and reasoning which was inaccessible before, and reasoning which now actually leads us to things like being able to perform part of taking a limit and then utilizing that to find some really interesting things.